Let's talk about advanced numerical methods for solving particularly nonlinear problems. So this sort of thing is common with fluid dynamics, especially when you include temperature, buoyancy, natural convection. You're likely to run into solver problems. So we're going to go over three different methods today. What the example that I'm using here is called buoyancy of water. The idea with this model is that we have a cold temperature over here, 283. We have a vessel that's filled with water in here. I don't know if you can see that red. And then on this side, we have a hot plate, which in my example is set to 313 for a delta T between the two boundaries of 30. And the idea here is that the water is going to be heated up over here. Maybe I'll use a different color. Heated up, and it's going to rise due to natural buoyancy. It's going to flow over here because once it reaches the cold, it's going to sink back down. And then it comes back over here to replenish that cycle. So what we're going to get is this convection circle that goes around and around and around. Whenever you get that natural convection in this type of situation, you're gonna run into numerical problems. Okay, so the first method that we're going to look at, actually I should demonstrate what happens if you just naively jump into this. You hit compute. All of the numerical methods kind of operate on the same idea. You start with an initial guess, that's your initial value, and you iterate towards the solution. But as you can see here, the fluid is very frenetic. The computer doesn't know which way it should go. You might also notice that the temperature is approaching the Big Bang, and in some cases even negative. So you know that your solver is off in la la land, and it's not able to find the right solution. So option number one to fix this is the numerical solver route. And the way you would get to that is you go under stationary, solver configuration, stationary solver, and fully coupled. We're going to talk more next week about what fully coupled means when we talk more about multiphysics coupling. But for now, what you need to notice is the nonlinear method, which is by default set to automatic Newton method. The Newton-Raphson method is one of the most common ways of root finding. We're going to be talking about this in numerical methods in third year. Basically, the idea is that, yeah, you start off with this initial guess and you step towards your solution. Well, there's another option under here called automatic highly nonlinear Newton. And when you select that, what you're going to be doing is you're going to be taking smaller steps. So it's a lot more controlled. You're less likely to overshoot and you're more likely to find that solution. All it's actually done, you might notice, is just tweak some of the parameters. So there's no magic happening here. You're just tweaking down the parameters. This is really more for convenience. And sure enough, when we calculate, we see much more robust behavior of this convective circuit as it is developed. And we find our solution. Great. The problem with this is that the numerical methods are never guaranteed for nonlinear problems. Even if you are guaranteed to find a solution, which you're not sure it's the right solution. It could be a different type of solution, a different route, for example. So you want to look at different ways. There's the other problem that this is for delta t of 30K. If you went up to 50K or 60 or 70, you still might not be able to find the solution, in which case you're either dialing down those settings even farther or you have to do other methods. So let's look at those other methods. First, I'm going to go back here. I'm going to undo that. So this is the case that died. And the idea here is, remember the description. The nonlinear solvers work by taking an initial guess and iterating on the solution. The better your initial guess, the more likely you are to find the solution. Makes sense. So the strategy here is that we're going to start off with a trivial solution, right? We're basically going to say the delta T is very, very small, approaching zero. If there is no temperature difference between this side and this side, guess what? You don't have a convective current. Trivial solution, you're guaranteed to find it. Then we're going to take the boundary here, delta T, and we're going to ramp it up. And we're going to take the solution from the previous step and use it as the initial condition or initial guess for the next step. And so we're going to build and escalate this sequence. The way you're going to do that is under stationary, you would define an extension, so it's down here, auxiliary sweep. This is going to look familiar. This is basically exactly a parametric sweep. What Console has done is added this as a study extension underneath this particular study. So instead of considering that you're doing a parametric sweep of a certain study, now you're taking a study and you're extending it in a certain dimension. It's a bit confusing. I'm not going to lie. It is what it is. Yeah. So just like we would do with the parametric sweep, we're going to select our parameter. So in this case, delta t is the difference between these two boundaries. And we're going to list out the parameters that we want to look at. So we're going to start off with 1e minus 3, which is effectively nothing, no convection. We're going to use that solution, and we're going to increase it to 1e minus 2, 1e 1, 1, 10, 30. The magic here is this continuation. And when we say that it's a continuation for the last parameter, what that means is we're going to take the solution from this one and use that as the initial condition for that one. You don't always want to do that with a parametric sweep, but in this case, because of the way we're using this technology, we do want to use that. That is the goal. Okay. When we enable this, we right click and we go to compute. And now you're going to see another feature popping up here. It's going to list your current delta t. So not only can you see this convective current develop, but if you're watching this, you're going to see delta t climbing closer and closer to 30, but it's going to have to take smaller and smaller steps. And this is reflective of the increased demand and complexity with this convective current as it's approaching 30K. You can imagine if we go up higher and higher and higher, this is going to have to take smaller and smaller steps. Good news for you, COMSOL's doing all that behind the scenes. You don't need to be bothered with that. And sure enough, it finds the correct solution. Great. Now, the nice thing about this one is that you can go past 30, you can go 40, 50, 60, 70, 80, 90. You can just continue on like that and build up basically an arbitrary one. Or even if you do crash and the solver isn't able to make some kind of a jump, you know when it's going to crash. And that by itself is sometimes all the solution that you can really hope for. Now, the last method that I'm going to talk about is by using the time-dependent solver. And the idea here is that you would have a time-dependent boundary condition on this side. So you would still have 283 fixed on this side, but now this is going to be, 283 plus delta t times some function of t as it goes from 0 to 1. You put that into a time stepper, and now it's going to start off at T0, which is 283, no convective current, and you're going to step in a quasi-static way up to whatever value you want. The downside to that, so you can still have your physics as stationary physics, right? Steady state heat transport, steady state laminar flow, which still means you have a velocity, but it's not accelerating, except for corners. Speeding up, I should say, not accelerating. But in this case, you're using that time-dependent solver to change the boundary conditions. The downside to this is that when you tell COMSOL to do this, you're going to start to change your equations that are going to be displayed, and that tends to be confusing. It's going to ask for additional material properties. It's going to show equations that reflect that time dependence, even though you're doing the quasi-statics. It's identical, right? And continuation is built in, obviously, for time stepping. But it's not quite so elegant. So for that reason, it's generally preferred to go for